lesson 931. I will say after lesson 922, that video was a fist fight and a lot of work. This one I think is a lot easier. So hopefully we do a little bit better with this one. So how fast is it going? Average rate of change in projectile motions. Essentially, we're just going to divide the change in y by the change in x. That's really what this whole video is about. So you've calculated the speed of a moving object by dividing the distance traveled by time. For example, if you drive a distance of 150 miles in an hour, in 3 hours, then your average speed is 50 miles an hour. You divide your change in y by your change in x. However, what if an object is not traveling at a constant speed? How can you determine the speed at any point in time when the speed is increasing or decreasing? So essentially what we're going to do is we're just going to pick 2 points and do the change in y over the change in x and let that be sort of an average. And that's what we're going to do. It's pretty simple. There's not a lot to it. So, water balloon velocity. Sasha used video footage from the water balloon contest in Chapter 5 and an app to record the approximate heights at specific times of Maggie's balloon. Her data is shown in the table at the right. Maggie's balloon reached a maximum of 90.75 feet, so you could see it was right after 2.5 seconds was the maximum. Or right before, I don't know, maybe it was already coming back down. How quickly did her balloon rise and fall? That is, what is the balloon's velocity speed during different times of its flight? Complete the parts below to measure these questions. So first of all, it wants us to graph these points on a scale and use a curve to your graph to model the data. What is the shape of the curve? Is it what you expected? Well, I expect it would do something like this. I apologize. I did not write down my numbers here, so I'm jotting them down really quickly, and then I will go ahead and do that. Okay, so let's go ahead and graph this thing. Jumping over to a coordinate plane. I just jotted down those points real quickly. I think it's hopefully obvious to everybody that this is going to be x in seconds, and this is going to be y in, I think it was meters of height, and it goes up to 90, so this is going to be by tens, right? So this will be 50 meters, 100 meters, and this seconds I'll just leave it. So it started at 0 at 34.2, so it's right around there. I'm sorry, 0 was 0, my mistake. A half a second was 34.2. 1 second was 60 meters. 1.5 seconds was 78. 78's right there. 2 meters was 88.4, so just below 90. 2.5 was at 90.5. 3 was at 84. 3.5 was at 70. 4 was at 48. And 4.5 was at 18. So you can see that we did get that kind of parabolic shape that we expected to see. Going back to B, it says the average rate of change is calculated by determining the slope between, and again, the slope is the change in y over the change in x, right? Slope is change in y over change in x. Is calculated by determining the slope between 2 points on a graph. For example, calculate the average rate of change for the balloon between a half second and 1 second. Well, my change in y, it went up, 6.1? So it went up 26.1 on the y, and it went up a half on the x. So if I divide 26.1 by a half, you can see it's about 52 meters a second. Because we want it for an entire second, right? We want a unit rate. We want it per one. We wouldn't say it changes much in a half second, even though it did change that much in a half second. But we're saying how much it goes per second. That's why we have to divide these two. It says choose 2 points from the table and use them to calculate the approximate velocity of a balloon in 1.75 seconds. Well, if I'm looking at 1.75 seconds, I think 1.75, it would make sense to use these 2 points, right? That's halfway between. And you can see my change in y is 10 and my change in x is 0.5. So 10 divided by 0.5 is going to be 20. So I'm going up 20 meters a second. Maggie's balloon landed after approximately 4.8 seconds. When did it reach its maximum height? Choose a pair of points and calculate the approximate velocity of the balloon just after it reaches maximum height. So if it landed at 4.8, I'm thinking that the middle should have been about 2.4, right? So 2.4, I guess I'm going about right here. Somewhere in between this. Obviously closer here than here, but these are the 2 points I have. So it looks like it went up 2.1 over 0.5. I divide 2.1 by 0.5 and I get about 4.2 meters per second. So you can see it makes a lot of sense. At the beginning, it's steep. It's got a fast launch. Then it starts to slow down, and eventually it's going to turn into 0, and then it's going to start going negative. And when it goes negative, it will start negative slowly, speed up, and then obviously faster towards the bottom. So what happened to the velocity of the balloon just before and just after it reached its maximum height? Does this make sense? Well, it was barely going up and then it was barely going down, just like we talked about. So yeah, it got really close to 0 as a positive, and then it started going negative. And if what we can do here just to verify that it's going negative is we can check these 2 points. What about between 2.5 and 3? Well, now it's going down. Let's see, let's make sure I do this right. I keep doing math in my head on these videos and missing it. So, I don't know why that's not. I don't know. This is kind of frozen up here. All right, so if I go 90.5, I'll be done. I don't know what's going on with this calculator. Is the number lock off? Wow. All right, so 90.5 minus. I'm sorry. I want to go the change. So I'm going to go this one first. 84.6 minus 90.5. So 84.6 minus 90.5. So it went down 5.9. And then this went up a half. So if I divide that, I get like negative 11.8. So you can see it's starting to drop. So it goes from positive to negative. And yeah, that does make sense because now it's dropping to the ground. What do you predict the velocity of the balloon will be just before it hits the ground? Well, I guess, it's kind of interesting. There's 2 ways. They told us it landed at 4.8, so I guess we could make another data point that says this if we wanted to, and we could say negative 18.8 and 0.3, and go negative 18.8 and divide it by 0.3. We could do that if we wanted. So negative 18.8 divided by 0.3, we're going to get negative 62 meters a second. Or I think they might have wanted us to use this one, and it's negative 30 divided by a half. And that would have been negative 60 meters a second. So either way, you could see it's 62 meters a second. It dropped 60 from here to here. It dropped 62 from here to here. But it was certainly speeding up as it hit the ground, which is, again, not surprising. Sasha, let's go ahead and I think I'm going to need to close this here and reopen it. Tell you what, I don't know what's going on here. My computer might need a good old-fashioned restart here, but it's acting up right now. I'm not sure why. I'll be I have lost the ability to write. Let me pause this and get back. I had a weird kind of deal there. I couldn't open programs. So anyway, hopefully that pause worked and I didn't lose all that video. So Sasha has a graph from Jen's balloon launch and knows that Jen's balloon reached a maximum of 96 feet. I'll tell you, we're not going to use this. They actually give us a resource page that looks way better than this graph, so we're going to kind of ignore this graph and use the resource page. But what we do need to know is what they want. They want t at 2 seconds, they want t at 2.5 seconds, and at 4 seconds, and at 0.1 seconds. So Sasha has a graph from Jen's balloon launch and knows that Jen's balloon reached a maximum of 96 feet, 32 yards, and landed after approximately 4.9 seconds. Sasha made a new graph with time in seconds and an x-axis and a height in feet with the y-axis. Use the graph to estimate the average rate of change at these. And it says, when is the height balloon increasing? When is it decreasing? How can you tell? Well, obviously it'll be when it's going up, it'll be positive, and when it's going down, it'll be negative. So I'll just answer question E right now. So let's go ahead and answer these. And again, we're going to hope that this program is going to let me open this. Nope. All right. Let's try this again. See if this thing is still freezing. All right, there we go. All right, so what I wanted was, I'm going to make this a little bit smaller so it all fits on one. I can view it all at once. Okay, so they want to know at t equals 2, that was A, B was t equals 2.5, C was t equals 4, and D was t equals 0.1. So at 2 seconds, you can see I'm right here, so I'll just use, I don't know, let's use 1.5 and 2.5. So my change in Y went from about, I don't know, 82 to about 97. So I would say my change in Y is about 15. And my change in X is obviously 1, which is kind of nice doing that. So I can say that this is about 15 meters a second because I'm just dividing by 1. If I'm at 2.5 seconds, well, if I'm looking for 2.5 seconds, 2.5 seconds is here, so I'm going to go between 2 seconds and 3 seconds. And you can see, I mean, I'm at about 93 and I go to about 92, so I guess it goes down 1 over 1. So I'd say it's losing about 1 meter a second, which makes sense. Pretty flat up at the top, not much is going on. At 4 seconds, I will go with 3.5, a lot going on here. Between 3.5 and 4.5. So 3.5 looks like at about 78. And it goes down to about 29. So it looks like I'm losing about 49 there. 59, 69, 78. Yeah. It's going down 49 over 1. So I'd say it's down about 49 meters a second. And then at 0.1, I mean, I don't know. I guess I can go from like a half. Half is about 18. So 0, 0, so it goes up about 18 over a half, which would be 36 meters a second. And again, you can see when it's going down, it's negative. Went down here, went down here. When it's going up, it's positive. That's really it. It's just changing Y over changing X, and make sure you realize this isn't always 1 here. So if it's a half or 2 or something, it's going to impact that change. So just be careful with it. So nice, short and sweet video for this one.